So Professor Park, this is your time, and then we invite you to start our astronomy workshop.
Okay, I just asked you one question about redshift of galaxies, and I found that you haven't heard of it yet, which is a bit embarrassing to me, but I try my best to deliver what I prepared for you today. My name is Changgon Park, and I work at a research institute in South Korea called Korea Institute for Advanced Study. I'm very excited to give a lecture to you, particularly to teachers. And today I have prepared a special lecture for you, which is not entirely on science, but this is science education, which is a good new challenge to me. Okay, so let me start with introduction to astronomy. There are many subfields of astronomy, and I have made a list of these subfields so that you can get an idea what astronomers are working on. So the first one is solar physics, solar astronomy, and this topic is about everything about sun, the internal structure and the atmospheric effect. And there are many people who are still working on this topic, even though this field is quite old, okay? and also mature. And there are a lot of things to do more. So people calculate the temperature distribution and energy production at the center, and they also calculate the internal turbulence and convection inside the sun. And also at the surface of the sun, there are many activities like sunspot phenomena, prominence, flare, and so on. And they all have great impact on the atmosphere and also magnetosphere on Earth. So that's very important topic. And the second one is planetary astronomy, and it deals with the upper atmospheric and magnetospheric phenomena on Earth, and also it includes the many planets, asteroids, comets, and so on. So basically, the solar system. It deals with solar system. And recently, this planetary astronomy expanded to study the exoplanets. So the exoplanetary astronomy has expanded significantly enough that we can classify that field as another separate topic. And the interstellar medium means the gas and dust between stars. And it has very close relationship with star formation topic, which is the next one. So stellar astronomy includes the formation of stars and also the evolution of stars, including the various phases of stellar evolution, like main sequence stars. Our sun belongs to main sequence stars, which means it's burning hydrogen at the center and produce helium. And there are other phases of stellar evolution, like giant phase and supergiant. And eventually they consume all the nuclear energy at the center to become compact objects, like white dwarf, neutron star, and black holes. And before they reach that stage, they become planetary nebula, or sometimes they explode to become supernovae. Okay. And there are also other branch of astronomy dealing with the groups of stars. And the star clusters like open cluster or globular cluster, and all kinds of stellar systems, including binary stars. I'm not sure if my terminology is too new to you. And if I say planetary nebula, I'm not sure if you have an image associated with this. Have you seen planetary nebula? No? Okay. It's a expanding shell of stars. So you can see the star in the middle, which used to be the core of star, and the envelope of this star is expanded. So if you type planetary nebula, and you can see many images on the web. And they can also, the massive stars can explode to become supernova. I'm quite sure you know supernova. Okay. And this dynamics of stellar system has close relationship with the structure of our galaxy, which we call Milky Way galaxy. And this galactic astronomy is a bit old topic. So it is basically replaced by the extragalactic astronomy now. But traditionally, this has been a very important field in astronomy. It deals with the structure and contents of the Milky Way galaxy. The contents means there are many. In our case, in the case of Milky Way galaxy, we have spiral arm, okay? And there are thin disk and thick disk and bulge component and halo component. And underlying this stellar distribution, there's also dark matter distribution. So that has been a very important topic in the history of astronomy. But people have moved this interest to other galaxies, and there extragalactic astronomy came. And people study the physical properties of galaxies, such as the mass and luminosity and color and all kinds of the population of stars. And galaxies also do have gas and dust, which is interstellar medium. And there are a variety of galaxies, and they have different morphological type, shape, I mean. There are spiral galaxies, and elliptical galaxies, lenticular galaxies, and irregular galaxies. And in each classification, there is full diversity in morphology. So people study these physical properties, and also the clustering of galaxies is a very important thing to calculate because they are related with cosmology. The galaxy formation and evolution is also a very important topic. We all want to know how what we observe now began with. Okay? So we want to know the origin of our solar system. We want to know the birth of stars. We want to know the birth of galaxies, first stars, and also eventually we want to know the origin of the universe. So that galaxy formation is one of the very active area of research in these days. If we go to larger or more massive scale, the galaxies cluster together to become a group of galaxies, and they are called galaxy group or galaxy clusters. And these galaxy clusters also cluster together to become supercluster of galaxies, and so on. So there is a hierarchy of galaxies which forms the large-scale structure. And recently, as the space telescopes were launched, we were able to see very deep, distant part of the universe. So which allowed us to study the high redshift universe. And there we are about to see the first stars and first galaxies, which is very exciting. And this is also so important that I classify this topic as independent subfield. So high redshift object. Cosmology includes, that's my field, and includes the early universe. Early means, the meaning of early, it varies from one person to another, but in cosmology, early means the really early time of the universe, like 10 to the 34 seconds in terms of age of the universe. So that includes the inflationary epoch where everything has started. Okay? So universe has started and it produces the density fluctuation. And we want to know these physical mechanisms and the physical condition of this primordial density fluctuation. And that field also includes the nuclear synthesis, where all these atoms have formed. That was when the universe was about 10 billion times smaller than now. Okay? And about when the universe was about 1,000 times smaller than now, there was cosmic micro background radiation released. This is the light that existed in the universe from the beginning, but at that time, when the universe was 1,000 times contracted, this light has separated, finished the interaction with other component of the universe, the matter, and becomes free and were able to propagate freely. So that one we call cosmic microwave background radiation, which we are still able to observe. So that has been very important topic in cosmology. That topic is getting a little old, but people are still working on it. The large-scale structure in the universe is basically addressing the distribution of galaxies on very large scale. And so to some extent, that topic belongs to extragalactic astronomy. But because this distribution remembers the initial condition of the universe, one can extract cosmological information from this distribution. So I classify this topic to cosmology. So if I classify the subfield of astronomy in terms of the subject or target on the study, this is the one way to classify them. Okay, this is another way to classify the subfield of astronomy. And here I divided astronomy in terms of the research style or research tools. And I guess everybody know that even physics and all other natural sciences can be divided into experimental science and theoretical science, right? So likewise, in astronomy, we cannot do experiment on the cosmic object, so we observe them. We observe them and take images or spectra. So these people we call observational astronomers. And people can use optical astronomy. So we go to telescope and on the ground and use and take the visible light or maybe slightly UV light or slightly infrared light. And there are also radio astronomy. So we can use radio telescopes or telescope arrays to capture radio frequency. And people can also observe slightly shorter wavelength part, which is called sub-millimeter, okay? And even shorter wavelength part, which is infrared. Okay? So that's infrared astronomy. People can also try to capture the high energy particles, which are basically gamma rays or high energy particles, and those fields are called high energy astrophysics. And a very different style is theoretical astronomy, and people can two different kind of approaches or both. And one is analytic approach, and the other one is numerical approach. So this numerical approach is called computational astronomy, and this field is getting more and more important these days as people get more and more data reaching the nonlinear state of the cosmic object. For these two, they have to be supported by two other approaches, and they are instrumentation and data science. Without instrumentation, observation is impossible. So you need telescope and you need a detector, okay? And someone has to make it in very close collaboration with astronomers. And it's best if astronomers become instrumentalists and make it. Okay? So the ideal situation is the following. Someone think of some new question about the universe or the cosmic object, and he thinks of how to or what to observe. And for that purpose, he can ask the instrumentalist to make specific instruments and telescope, okay, and make it, and also carry out observation for many years and get the data. And this data goes to observers and also theorists to analyze this data and finally get the answer. Okay? And this cycle may take 10 or 20 years or even 50 years, but that's the ideal situation. But in that cycle, it's critically important to have very close collaboration with instrumentation. So we need to build telescope and photometric detector to get images and spectroscopic detector to get spectra. Okay? And one can fly all these systems to the space, okay? Which is called space astronomy. So space astronomy is also getting very important, and we will soon get a huge impact from space astronomy. Data science is really growing fast because the amount of data is increasing very quickly. Because of this massive data requirement, we need to have not only this big data storage system, but also the technology to mining and handling this data are getting very important now. The computer simulation is, of course, is really growing fast. So in many fields in astronomy, the simulation makes a critical role in terms of explaining what has been observed and also predicting what will be observed. And I'll give you a couple of examples in the later part of my talk. And this big data analysis, the performance of computer is critically important now. So we need to have or upgrade your computer quite frequently. So with these 4 tools, you will be finally able to work. So in my case, it took my entire life to build these 4 tools. And now I'm about to be able to work very efficiently, but I soon have to retire. So that's very that's unfortunate, but I'm just emphasizing that how important to equip all these 4 tools to do very competitive research. Okay, so that's very brief introduction to astronomy. Do you have any questions? Maybe a little too early? Okay, you can interrupt me anytime you want. By the way, is my pronunciation and the speaking is okay? Okay. I'm trying to I'm trying to be slow. I usually speak a little faster than this. Okay. Astronomy stands on the application and feedback of all 4 approaches. So that's important. Okay, so let me mention the impact of astronomical sciences. So I listed a few things, more than this. The first is fundamental science. So it's not, well, to first stage, it may appear it's only fundamental science, but there are many applications of astronomical sciences in other applied science and engineering. But within fundamental science, it also has a great impact on the other field of natural science. So it contributes to development of astronomy, of course, and astrophysics, physics, and earth science and space science, and so on. And all these have very tight correlation. And as I said, astronomy always is dealing with big data. That indicates that how important or how much impact this astronomy has on other, because we deal with big data. So supercomputer technology and big data manipulation and data mining and AI, these days AI-related science, I personally don't use AI because I'm not really relying on this machine. But this young generation, young people, young astronomers, there's a lot of young astronomers using AI in their research. And astronomy is a workhorse for high-tech technology. And I guess everybody has phone, and the phone has camera. And the CCD and CMOS images have been mainly developed by astronomers in the beginning. Okay? Because we had to detect very faint light from distant cosmic object, and we need very sensitive detectors. And the astronomers have been using film, okay, long time past. And the quantum efficiency of film is at most 3%. The amount of reaction with respect to given light, but the quantum efficiency of CCD can be above 80%. So with the same telescope, it is like having 100 times bigger telescope. Okay? The telescope didn't change, but just changing the sensitivity of the detector, it is equivalent to have 100 times bigger telescope. So it's a revolution in astronomy. So there's a lot of astronomers spending time to develop and use CCD image detectors in the past. So, and that drive the development of these detectors. So it's the indirect impact, but still it's a very important contribution of astronomy. I'd like to also emphasize astronomy, the fact that astronomy is international. Okay? Because unlike all other science, or maybe this may be too much, but we are sharing the target. Because the sky is turning. So nobody monopolizes any part of the sky. Okay? Of course, we cannot observe the southern part. The Korea is located at the latitude of about 36 degrees in north. So to observe the southern sky, we have to go to Chile or Australia. Okay? And also, I guess you know, the Dutch have built first telescope in Indonesia in 1920s, and the reason was to observe the southern sky. Okay, so there is some regional limitation, but still it turns from east to north, so it goes over the world. So by nature, the astronomy is international science. So there is no politics, no geological discrimination and anything. So it's very easy for astronomers to collaborate. So it's a very common, in most astronomical observatory, when people build a new telescope, about 10% of time is given to the local research institute, and a large fraction of the remaining time is open for the astronomers in the world. People can make an application for the observing time, and they give time to these people in other countries. So this has been our tradition, and also we are here to propagate astronomy to other countries, including Indonesia, and because we have been benefited from this, the nature of astronomy, which is international. So I'd like to emphasize this, and each country can grow science very fast through astronomy, because there is international collaboration is very easy. And as you know, astronomy is a very good topic for science education. So because we have many beautiful images of stars and galaxies and interstellar medium, which can easily attract people to science. And the last one is also what I really want to mention. Many countries in the universe, I guess in principle, all area in the world has astronomy tradition. And I heard in old Indonesia, you had astronomical calendar for farming, for rice farming. And also the temples are aligned with respect to celestial directions, which is also application of astronomy. So I guess someone have to work on this to recover your tradition of astronomy. And the science in the past has to be connected with the science at the modern time. So you are not really starting from nothing, but you are succeeding to the science you had in the past. And only with that, you can increase your potential significantly. Okay. And astronomy, unlike other branches of science, usually have a long history in all communities. So I recommend you to study the history of astronomy in Indonesia, okay? Before 20th century, before 20th century. So that's the impact. There may be more, but I'm just mentioning 6 of them. So let me mention a few recent developments in astronomy. And here I may have some difficulty because you don't seem to be familiar with astronomical terminology or concept. So, but I try, and you can ask questions anytime. Okay, I'm showing you a very difficult figure, which may be very time-consuming for you to understand. So let's first look at the left-hand part. So the universe. So this is a standard picture of the universe, which people first have to know, but secondly, you shouldn't believe this. Otherwise, there will be no development. Okay? So this is just model we have right now, and it can be updated anytime in the future. So according to the standard picture of the universe has an age, which means in time, space, it has finite past, but it has infinite future. So the universe was born 13.8 billion years ago, but will last forever in the future. Okay? So that's the picture we have in time. And in terms of space, the universe is infinite. So there will be no limit. And also, everywhere is equal. For example, if you take 3 points, any 3 points in space, and connect them with the shortest length, okay, then it will form triangle. And if you add the angle formed by 3 sides, you will get 180 degrees. That is when the universe is geometrically flat. Okay. If you add this angle and get angle sum greater than 180 degrees, then you will find that this universe has positive curvature. If it's less than 180, then it has negative curvature. But according to the measurement, until now, we find the universe has zero curvature, okay, or the flat geometry. And when the universe is flat or zero curvature, it has no boundary. It has infinite size. It has infinite size not only now, but also in the past and also in the beginning. So the universe has been always infinite right at the beginning and will be infinite in the future too. So this is a picture which most people don't understand and misunderstand. Many people hear that universe has started from infinitely small size and expanded to become larger and larger. And that is a completely wrong concept of the universe. That's not the standard picture of the cosmology right now. Universe has been smaller and smaller in the sense that any 2 points, the distance was closer and closer in the past. But the universe has been always infinite. Okay? So that's the picture we have on space. So universe is expanding, and it's even the expansion is accelerating recently. It has been decelerating in the past. I mean, these 2 points, if you look at these 2 points, this point has been receding to each other, okay? But the rate of receding speed was decreasing. So it is still getting farther and farther, but the speed was getting slower. But recently means about 8 billion years ago, it started to get accelerated. So the rate of the receding motion was increasing recently. Okay? So the expansion history of the universe is a bit complicated, so I won't tell you too much about it. So it's true that the universe is expanding, but this expansion has very complicated scenario in the past, and maybe in the future too. So universe, so the space is flat and therefore infinite, and therefore it has to be infinite all the time, and is expanding, and recently this decelerating expansion has converted to accelerating expansion, okay? And the things inside, the matter. So I call all kinds of forms of energy as matter, okay? So the radiation, the photon, this gamma means photon, and nu means neutrino, okay? So universe is filled with photon, neutrino, and baryon. Baryon means all kind of atom you see, okay? And something you haven't identified yet, but you notice they exist, and they are dark matter and dark energy. So the major component, the mass component of the universe are, in terms of the importance, dark energy takes 70%. Look at this Venn diagram. 70% of the matter component of the universe is dark energy, and secondly, dark matter, okay? And thirdly is baryon, which I put atom there, and then radiation, okay? And then neutrino, in terms of the fraction of mass. And this matter is not uniformly distributed. At some place there are more matter, and some place there's less amount of matter. And the place where there are more mass, they get contracted by gravitational force and form various cosmic objects like galaxies and stars. And you can easily ask how this density fluctuation has started. Okay. So we say on very large scale, the very large means 100 megaparsec scale. Do you know parsec? The distance unit, parsec. Maybe not. Okay. Do you know light year?
Yes.
Light year. Okay. So that's the distance which light propagates during 1 year. Okay. So the 1 parsec is about 3 light year. Okay. So you can consider it's almost the same. Okay. It's 3.26 light year is 1 parsec. On very large scale means about 100 million parsec. Okay, so that's 10 to the 8 parsec, which is a few hundred million light year. So above that scale, if you smooth the distribution of galaxies over that large scale, you see the matter distribution. I mean, all kinds of galaxies and light, neutrino, and all those things. They appear uniform. Okay. But on small scale, of course, there are interesting variation from one place to another, and these fluctuations we think has been seeded in the very early universe, and that epoch we call inflationary epoch, when the universe first started. Right after the beginning, there was a phase of universe where the space expanded exponentially, and the initial density fluctuation has been created. So, and many physicists and astronomers are working on each part of this element of standard picture of the universe, and this is the picture we have right now. It took quite a long time to get this picture. So when I was a graduate student in early 80s, we didn't have this picture. Okay? There is individual ideas, but it has been only the late 1980s this idea first get assembled to give us one single grand design picture of the universe, and that cosmology in 1980s turned out to be wrong. And there has been a few transformation of this cosmology, and this is what the cosmology is at the moment. Okay, so that's only the left part. Okay. So let's look at the right-hand side. Okay, this is a combination of drawing and actual data. Okay, the dots are actual galaxies. The dots in the middle with the wedge shape and the actual data from Sloan survey. So imagine the entire universe. Okay, I told you the universe is infinite, and we are located one particular point in the infinite, within infinite space. Okay, and then you look around the other place. Okay. How much can you see? Remember, the universe has an age. It has been existing for 13.8 gigayear. Okay? And the speed of light is finite. So there exists the maximum distance you can see, where this light has started right in the beginning of the universe and traveled for 13.8 gigayear and just arrived. So that's the maximum distance you can see. Even though universe is infinite, you can see only this spherical, the inside of this spherical volume. And that frontier surface is called Big Bang surface, or the particle horizon. Okay? And that's the farthest distance we can see at the moment. As time passes, the region behind will reach us. So as time passes, our visible part of the universe is expanding. I can see more and more. So this is the maximum distance we can see. And that's where the light has traveled during the age of the universe. Okay. And beyond, we cannot see at the moment, but we'll be able to see in the future. So if we are God, we can cut the universe all at once, and we can locate ourselves here, and at some distance there will be Big Bang surface over there, and we can see our place and the Big Bang surface at the same time. But that is not possible in practice, because all we can do is just observe, and the information should be carried by light. Okay? So as you see farther and farther, the photon took more time to arrive us. So as you go farther and farther, you observe this part of the universe more in the past. Okay? So we are here. This is not only here, but also now. Okay? So if you observe this galaxy here, and this galaxy is this much separated from us, but also this much in the past. Because the light from this galaxy took some amount of time to reach us. So this is the past. So as you go further and further, okay, so by the time we see these places, we are looking at the beginning of the universe. So in principle, we can see beginning of the universe now. In practice, we cannot see, because at this time, the matter in the universe was fully ionized, and also the atoms were broken into more elementary particles. So the light has been interacting with other fundamental particles, so that this light has been scattering a lot, and we cannot see behind. Just like the cloud. So suppose there is sun over there, and we know sun is round. Okay? So we want to see the sun, but if there's a cloud which scatters the sunlight, then all we can see is the bottom part of the cloud, right? So the sunlight hits the backside of the cloud, and this photon scatters a lot, and then they reach the bottom of the cloud, and there's no water vapor to scatter. So the photon makes a free travel to us, and we are able to see the shape of the bottom of the cloud, but not the shape of the sun. Okay? So likewise, the matter at this time were interacting with the photon too much, so that we cannot see behind. Okay? So all we can see is the volume of the universe up to this point, where this photon stopped interacting with other particles, just like the bottom part of the cloud. Okay, okay, so this picture shows a slice of the universe along the past light cone. Okay, so it is a space-time cut, which is a bit difficult to understand. But if someone able to finally understand, it's a great thing. Okay, because your thinking is not only in space but also in time. Okay, so. Okay, so that's the standard picture of the universe, which cosmologists have been working on for more than 50 years, and well, almost 100 years to reach this point. And this is about to change. I'll mention a few revolutions in astronomy these days, just a few, and there may be more by Professor Jung-Ju Son later, tomorrow. Let me first mention this one. The first, a new era. So the new era of observational astronomy is around the corner, and the first one is astronomical imaging is about to end. This is a bit too extreme comment, because even on the Earth, most people in the past used the map. Okay? So when I visit, for example, when I visit Jakarta and Bandung, I would look at the map and figure out where these cities are and when this university is. And these days we can go to Google Map, okay, just to, this very convenient way to see all the geological information. Okay. Likewise, the LSST or Rubin telescope will observe the sky and they will put up this 10-year movie on the web. Okay? So for most purpose, now you don't have to go out and use telescope to observe, to get images. So the images will be there. Okay? For very special purpose, you may still need taking images, but for general purpose, the imaging will be done by this. This is not only just taking the standstill picture of the universe, but they will take it for 10 years. So all the variable or transient phenomena will be observed too. Okay, so that is one thing. Another one is, so unlike imaging, the era of spectroscopy is coming. So, of course, astronomy has been doing spectroscopy already for more than 50 years, but really massive spectroscopy, just like the imaging observation in the past, is coming now. And people will be getting this three-dimensional data. So this black photo at the bottom is, for example, the image you usually get using imaging detector. But at every pixel, you will get spectrum. Okay? So you will get 3D data cube. And that will, I expect, that will also come to your mobile phone. So now you get image. And in the future, you will get this 3D data, okay? And you'll find out all the physical properties of people, okay? Third, the era of extremely large telescope is coming too. So the size of telescope the people use in astronomical observatory is usually larger than 50 centimeter, and the small ones are usually 1 meter or 2 meter class. Okay, and intermediate size can be 4 meter and 6.5 meter telescope, and the biggest telescope at the moment is about 8 meter or 10 meter telescope. Okay, and now there are a few large telescope projects going on, and they are like the European Extremely Large Telescope (ELT), and the aperture size is about 40 meter. Okay, I remember they initially aimed to have 100 meter telescope, and that may have been too much. 30 meter telescope, by definition, it has aperture size of 30 meter. And GMT, Giant Magellanic Telescope, and the diameter is 25 meter. Okay. And GMT is what Korea is participating. So we are going to get about 10% share of this telescope. And there are also other existing telescopes as well. So all these extremely large telescope will be operating. Well, it was originally planning to start this decade, but well, I guess they will come next decade, which is not far. Okay, and that we should prepare for this new era. Let me share one slide showing how the redshift survey of galaxies in cosmology has been expanding. Okay. So this is the simulation showing a part of the universe along one slice. Okay. So suppose you are looking at the night sky and drew a line, okay, from here to there, and observed all the objects along this line. Okay. And then plotted it on the paper, and that will look like a wedge diagram like this. And your survey will end at the distance where this Big Bang surface is. You cannot see beyond. Okay? So H on the right is the horizon of the universe, and we are on the left corner. Okay? And this little circle is the depth of the largest survey when I was a graduate student in 1980s. And so if you look at the history of the universe, so before redshift 0.6, you told me that you don't know what redshift means. So the redshift appears because the universe is expanding. Okay? So look at me, okay? And we are this much separated. And suppose the universe is expanding. It is actually expanding. So as time passes, the distance between you and me will increase. I'm not moving and you are not moving, but the space between you and me are increasing. So you will get farther and farther apart as time passes. And if I move very fast, then you think that I appear redder because the photon bounced my face and went to you will get redshifted because the space is expanding and the wavelengths will get longer and longer because I'm moving back. Okay, so that's why we call this phenomena redshift. Okay, so the redshift means this phenomena, but it is also used as the time coordinate because as you move farther and farther, the more distant part is moving faster and faster. Okay? Let me give you one example. Okay. So according to our standard picture of the universe is expanding uniformly. Uniformly means the rate of expansion is the same everywhere and any separation. So between me and this you will be maybe this is about 4 meters, okay? 4 meters. And the person way in the back will be maybe 10 meters, okay? And now certain amount of time has passed, okay? So 1 second has passed. And if I make the rate of change the same, can I write here? Say the distance is L, okay? And at some time later, so now delta t has passed, and the distance between 2 points has increased. Right? So the distance becomes L plus delta L. Okay? Yeah, I got the pen, so it's okay. And the uniform expansion, the uniform rate of expansion means the fraction the fractional change is the same, okay? And of course, it will be proportional to delta t. So as more time pass, there will be more separation, okay? Right. So if you move this delta t to the left and move L to the right, then you will see delta L over delta t will be proportional to L, right? And delta t, we call the velocity, right? So between me and you, it's only 4 meters. And between me and the person in the back will be 10 meters, which means, well, suppose it's 8 meters, okay? Then you should be moving twice faster than her relative to me to keep this ratio the same. The fractional change and the distance is the same everywhere, okay? And that is called Hubble-Lemaitre law. I guess you are teaching this law to students, right? And this is coming from this uniform expansion. And therefore, as you look farther and farther part of the universe, they are moving faster and faster, which means the redshift is more and more. And therefore, the larger redshift means more distance and higher receding velocity, and also more in the past. So redshift can be used as the time unit. And when redshift 1000 means, when we say redshift 1000, that means the universe has been 1000 times more contracted, smaller, because redshift is directly proportional to the rate of stretching the wavelengths of the light. Okay? So I hope you understand what redshift means and why we use redshift as a time coordinate. Okay? Of course, we can use time directly. So this is the time measured from now to the past. So it ends at 13.8 billion years. Okay? Because this is the beginning of the universe. As I said, there will be more space in the back, but this is just what we can see at the moment. So my time coordinate stops at 13.8 billion years, but there's a corresponding redshift coordinate here, okay? And there is more and more redshift, and it stops at redshift infinity. Okay? So it's infinitely rather. Okay, so this is not what I wanted to show you. I wanted to show how the survey has been expanding. And in early 90s, there was Sloan Digital Sky Survey, which was observing all the galaxies with the apparent R-band magnitude brighter than 70.77. I'm not sure if this makes sense. When I say 17th magnitude, you know, people can see the stars up to about 6th magnitude, right? I can see up to about 4th magnitude, but you may be able to see maybe 6 or 7. I heard that Mongolians can see even fainter stars, but that's about human can see. But so 17th magnitude is a pretty faint one. Well, these days, telescope can observe much faint one. But this is a spectroscopic survey. We get the spectrum and detect these emission lines and measure the redshift. We know the rest frame frequency or wavelengths, and we measure the wavelengths this emission line or absorption line is measured, and then calculate the redshift. And they reached about 0.1 in terms of redshift, and you can see this is about a little bit 1.5 billion years in the past. So this is the amount of the universe we observed in 1980s, early 90s. And this survey made a deeper and deeper survey. And SDSS-2, this is the old galaxies, and this is a special red galaxy. They went deeper for red galaxy. And this is when SDSS-3, they went to about redshift 0.6, and that was about 10 years ago. Yeah, 10 years ago. And right now, EBOS has finished too. So EBOS is very recent, a few years ago. And now DASI and Euclid is the satellite. It's a European satellite space astronomy mission. And DASI is ground-based mission, and they are reaching deeper. So for regular galaxies, they reach redshift 1, and for emission line galaxies and quasars, they reach about 2, and for quasars, they go beyond. So my point is, people are observing more and more part of the universe. And now you can see the significant fraction of the visible part of the universe is being observed now. Okay? And recently, the JWST Space Telescope has been launched, and they are observing up to 20. It's not spectrum. Well, they also have spectrum spectrograph too, but very low resolution spectrograph. So there should be a lot more spectroscopic observation in the future. And also this JWST telescope can observe only a very small part of the sky. So there should be a lot more imaging observation too. But we are beginning to look at up to this part of the universe right now. Okay? I'll show you a few examples. Okay, so that was the, what I would say, revolution of observational astronomy. Okay. The next topic is a bit difficult, so I'll skip that part, except just mentioning it. This is one of the research I have done. I guess everybody knows what I'm showing, right? There is early type galaxies, elliptical galaxies, and lenticular type galaxies, which is a disk, but there's almost no star formation. And there is spiral galaxies with or without bars, and there's irregular galaxies. I also learned that galaxies has different shape when I was high school or undergraduate students in the past. Nobody told me why they have to have this shape. So I wanted to know this ever since I was high school students. I wanted to know why they have this shape and what shape galaxy has when they first born. Okay? So this is the one question I had. Okay? The morphology of the first galaxies. When galaxies first form, do they have one of this shape, or did they have all different kind of shape ever since in the beginning? And of course, the study wasn't possible in the past, so I used my simulation. So we made a very large cosmological simulation, and this is a very small part of my simulation. And I said this is only one part in 100,000 of my simulation. Okay? And you can still see the formation of galaxy cluster. All these things are one galaxy, you see. Okay? And the white dots are stars, and these colors are gas. And what can you see? I guess you can agree that most galaxies are spiral galaxies, having disk. So we found that this is pretty early period, and we looked at the evolution of morphology of galaxies at very early universe to recent universe, and we found that galaxies has disk type in the beginning, and there are only small fraction of galaxies having elliptical shape or irregular shape, and their morphology is transient because these disk galaxies sometimes get merged or make very close encounter, and their structure destroyed. And temporarily, they have this kind of spheroidal shape or irregular shape. But as time passes, they recover their disk morphology as more gas comes in with angular momentum. So galaxy first has disk shape or remain disk, but also they can change their morphology briefly to spheroidal or irregular type, but they regain their disk morphology later. So majority of galaxies in the beginning, galaxy has disk type. And this was found 2 years ago. Only theoretically in simulation. There was no observation. Actually, everybody in observation and simulation was opposite to my discovery. Observation from Hubble Space Telescope indicate that the galaxies in the early universe are mostly spheroidal or irregular galaxies, so which is inconsistent with my finding. And all the simulations by major group in the world, they also predicted the galaxies at the early time was either spheroidal or irregulars. So the epoch we are looking at is, this is very incorrect illustration of the universe, but this is very popular way, because I told you this is not the picture of the universe. Universe didn't expand from a point. This is a completely wrong picture. But anyway, so we are here and we are looking back, okay? And as we look further and further, the time is also the earlier and earlier. Okay? So this is trying to show that the JWST now is looking at even further back, and we are looking at the first galaxies. This is a few of the part of the sky this JWST space telescope has observed, and we looked at all the galaxies. I mean, the object without spikes are all galaxies, and we measured the shape of the galaxies to find that about 70% of galaxies are disk galaxies, and about 15% as spheroidal or irregulars. So this confirms, the observation confirmed our prediction from simulation. So this is a great achievement we were able to make using cosmological simulation. And also it solved my long-lasting question, which I had for 50 years. So my question mark turned to exclamation mark. Another interesting question is this. So there are many detectors and observation program on JWST, and one very interesting thing is these high redshift galaxies. Again, the high redshift means, this is the redshift, high redshift means early epoch of the universe. So before JWST, basically we are not able to observe any of these galaxies. Each point is galaxy, okay? And this is the brightness or luminosity or absolute magnitude of galaxies. So as you go high, is more brighter galaxies and fainter galaxies. And as you go to the right, this is the galaxies sitting at farther and farther, okay? And it was shocking to every astronomers to be reported that JWST observed galaxies at this only. Okay? And this is challenging to cosmological models, which didn't predict this kind of galaxies at this only. So in the early history of the universe, galaxies, massive galaxies, and also the black holes have formed already and observed. And people are trying to explain this. Without changing cosmology, they change how stars form, how galaxies form. So they change this astrophysics to explain this new observation. In many lectures of mine, I prepared these 2 pages summarizing the history of cosmology during the past century. And I was never able to explain this, because by the time I reach this slide, my time is already over. So I'll again skip this part. But let me just mention this one thing, okay? So the standard cosmological model, which I explained to you, was this one. And that is called the concordance lambda CDM model, where the universe is filled with photon, neutrino, baryon, and dark matter, which is cold, and dark energy, which is a cosmological constant, or the energy of the vacuum. And the fluctuation was created in the beginning during the inflation epoch, in the very, very early time of the universe. and the universe has been expanding, and the structures grew out of this initial fluctuation to become stars and galaxies through gravity. So this stands for gravitational instability through gravity. So that is the complete picture on the contents and evolution of the universe, regardless of whether or not it's correct. We have a complete picture. Okay? And now that we have a strong doubt now on this dark energy, okay? The nature of dark energy. So there's a lot of work on dark energy, and the standard picture seems to be a bit in error. Okay? We are working on it. So to close, let me. So I have only one page left. So let me show my opinion on how to educate students so that they can grow to be scientists. And of course, this may not be practical because this is just ideal way to educate students. Even when I was a student, I didn't like teacher who says anything they teach is not clear. They explain something, and at the end they say, you shouldn't believe this. Okay? The students want to hear about only fact so that they can remember, okay? And also solve problems. But in science, nothing is fact. Nothing is absolute. It's all models. You said you're teaching a Keplerian law, and you must be teaching Newtonian gravity and so on. They're all wrong. Okay? They're all wrong. We know they are wrong, but they work in practice. And that's why we teach, and that's why we study. But in principle, all of them are wrong. Einstein's general relativity, we know is wrong. But it's more accurate than Newtonian gravity, so we teach and we study. And also we apply this to the motion of satellites and so on to get better accuracy. But in principle, it's wrong. But if you teach students in this way, they will get crazy. And they will be lost and don't know what to study. Okay? So we should decide what to do, but I'll just tell you the ideal way to educate. So let me define scientists as people who are making new findings and creating new knowledge in nature. So to do that job, the scientists should not grow by just learning what is already known. So they should hear about what is unknown, and they should be encouraged. But in most education, the students are dumped over too many little knowledges to remember, and they quickly spoiled by this task. So students have to solve problems, they have to memorize all the unnecessary or not too necessary facts, and they never have time to get energy to find out something new. So I hope teachers need to teach what is unknown yet, in addition to what is already known. And the amount of teach about what is already known should be minimum. So that students need to be encouraged to go after making new discoveries and better, not spoiled by too much knowledge. And that is because scientific theory is not a collection of absolute fact or truth. So scientific theory is just a set of models that works well to describe what we experience in nature. Okay? And this has been a great shock to me. When I went to the university, And in the fourth year, or third year, fourth year, I start to study general relativity using Weinberg's textbook. And that book completely destroyed my picture on physics. Because all this Newtonian or special relativity works locally. And that was a great embarrassment to me. And that opened a new world toward the finding new things in nature. So as I said, Newtonian law, GR, and you heard that universe is expanding. I told you expanding. Nobody saw universe has been expanding. Okay? I told you universe is accelerating because of this negative pressure element, which we call dark energy. But dark energy is a device we added in cosmology to explain some observation. It's not absolute fact. It's a model. Expansion is also a model. You see, you measure the distance of the galaxies, and you found that the farther the galaxy is located, they'll appear redder. That's the observational fact. Expansion is introduced to explain this. So expansion is a model. It can be different things, but it's hard to think of other alternative. So it is accepted by all the astronomers now. Okay? We tried many different explanations, and all these other alternatives turn out to be wrong. So we now believe that, but still, it's a model. It's a working model. And if someone wants to find something new, you shouldn't absolutely believe in this. And that's what students have to be led in that way. Okay, so they should go out and get in touch with the real data. Okay? So most students are taught too much. So at very early age, they accumulate a lot of acclamation already. Before they start to ask questions, they already get the answer. But you remember when we are very young, okay, particularly in my age, we didn't have any science books when I was young, when I was elementary school student, not even science books. There was no books, okay, around mine. And when I was in undergraduate or even graduate school, there was no cosmology book in the world. The cosmology book, textbook appeared only in late 90s, okay, and so on. So what we had to do was just go out and accumulate questions. You just wonder why they look like that and how they start to be like that in the beginning. So you accumulate a lot of questions, and it's a great fun to change these questions to exclamation mark as you live. And that is a source of energy to continue research. So I hope you to, again, I'm telling that this is not practical to students who have to pass the exam and enter the university and so on, but at least you have to give a hint to them. Okay. So the last thing about the view on nature. The modern science has born in, I think, 16th or 18th century out of the philosophers in Europe. And they define this science as the pursuit for the absolute knowledge, the truth, which is universal and permanent. So you have some natural law of the universe, and you think that this works everywhere. And also it works always. Okay? So that's universal law, which is permanent, is the goal of the pursuit of scientists, which is not correct. The nature has two phases. It is local, the aspects of local and aspects of global or universal. It has an aspect of permanent, but also temporary and transient. So you have to capture both. But we are emphasizing too much on only one phase, and that has to be fixed. So let me show you this very simple diagram. So the natural, if you see natural phenomena, and there is aspects of universal and immutable, but there is also aspect of special, peculiar, and transient and variable. And this modern science, well, a little before modern science, because modern science is now emphasizing this part, this aspect of the nature. The traditional science defined by this European is emphasizing this part too much. Okay? And they call this one as the natural law. But the value of the left-hand side is here. Here, there is reservoir of new things. Okay? There can be new hidden law, which can be classified to this side later. Okay? And also, there is extra knowledge. The diversity of this natural phenomena contains a lot of new things and also it's an integral part of the nature. Okay? And also, this uniqueness gives you the value. And that also applies to everything. So each of us, all of us, we are breathing, we have two eyes, and one nose, and one mouth, and so on. So we all look the same. So maybe to aliens, we may not be distinguished. But in practice, each of us has our own special character. And we are all peculiar in some sense, right? And our life from one time to another is always changing. Our mind is fluctuating and so on. And this gives us the value of life. And that's why we can justify individual's life, because we are all making different life. So and that also applies to nature too. Okay? The plant in Indonesia and the plant in Korea, even though they are same species and same breed, they are slightly different. And that's interesting, and that may give us something, new knowledge and new law. Okay? And that is a very important aspect of the nature, and we should tell this to students in the future. Okay, so it's my great pleasure to give a lecture to you. Thank you very much.